Okay, so I've got this fancy title because I was asked to provide a title. So alternative titles were A Game of Threads or A Song of Asyncs and Awaits. I'm Renaud, for those who don't know me. I'm currently the iOS lead at Drawboard. We do PDF editors mostly, apps around that, and yeah, we very much care about concurrency. We very much care about these things because a PDF editor needs to be very responsive, and so we try to do a lot of I/O and asynchronous work so that the experience of users is as good as possible. So we care about Swift Structured Concurrency, which is a really neat technology that shipped in the last couple of years that everybody's probably pretty familiar with right now. So I want to do a survey, first of all. Who is currently shipping any production code with Swift Structured Concurrency right now in the room? I know there's not many people because it's raining hard, but okay, Amy is the only one, I guess. Do I see anyone else? So it's like, yeah, it's surprising. I would have thought that maybe a few more people would have lifted their hands, but we only have one person. But yeah, it's...
I use just threads, DispatchQueue, nothing more than that. Is
Yeah.
this a special package? I just use DispatchQueue and quite happy about that.
Yeah, that's GCD, right? But Swift Structured Concurrency is a new task and async await syntax that shipped like last year. And so it's been adopted, I guess, slowly by the community, even though it's pretty mature already, I can tell you already. And that's not what the talk is about. But anyway, another question is like, who has experimented with it? So not necessarily ship anything with it, but yeah, you've dabbled with it, you've played with it, you have experimented with it, which is good. And then who is planning to use it in the future? And yeah, like, I mean, I expect the whole room to leave their hands. It's pretty much like becoming universal. It's a fundamental thing, technology to use in the future, hopefully. But yeah, like people need to obviously get familiar with it and know as well the pitfalls. And tonight I'm going to talk about one of the pitfalls. But before that, let's just introduce a few things, right? So obviously we all know about async await syntax. It's a new syntax, new keywords. It makes writing asynchronous code very easy to write and read. It's really great, but I'm not talking about that, right? What I mean is that Swift Structured Concurrency, if you think about it, first of all, it's a low-cost abstraction for asynchronous work. It's not a zero-cost abstraction because it's impossible to do zero-cost abstractions for asynchronous work, but it's a low-cost abstraction. There's both the language that comes with it, but there's a runtime that is hidden from everything, right? But we have to remember that there's a cost to Swift Structured Concurrency. And because Swift Structured Concurrency has a lot of syllables and already I'm struggling, I'm going to refer to it as SSC from now on. So if I say SSC, that means that. And something to understand as well is that the implicit goal of SSC is to encourage you to use asynchronous paradigms and to maximize the use of threads and CPU cores and all of these things, right? So because the syntax is so much easier to use, the result should be that more work is being done on more threads, and therefore all the nice cores that Apple is selling are used in a better way, rather than having everything run off the main thread. So that's an implicit goal. They say it in some ways, but it's something to really understand about SSC beyond just the nice syntax. But obviously, running code concurrently is very tricky and dangerous. Like we probably are all aware that there's lots of problems with it and dangerous things. And so thankfully the language and the compiler are full of helpful diagnostics and is able to catch most of the common errors that SSC can introduce with your code. It's not perfect yet. I'm sure Swift 6 is going to have more warnings down the line, but already it's getting pretty good, obviously. So SSC is more than just async await. It is a package of goals and technologies that make a whole thing. It's not just a language and some fancy keywords. So it's important to understand. But now going back to who we are mostly iOS app developers, I'm sure. And what we really care about most of the time is really just this thing. Is my app running on the main thread or not, right? Sometimes we really care about being on the main thread because we, for example, want to update some UI properties, and if we don't, then we're going to be yelled at by the debugger, hopefully, or things are not going to work. But likewise, sometimes we want to make sure we don't run on the main thread because we do some heavy I/O, and we want the UI to remain responsive. So that's most of our our thought process when we start using concurrency and thinking in a concurrent way. That's really the problem that we're trying to solve. So in the olden days, this is what we did, right? We just had the old nice syntax with a closure. We have an async call that has some kind of completion handler that is invoked when that is when the work is complete, giving you some kind of result. And you can do something with that result, but we're all familiar with the fact that this is kind of brittle. We don't know anything, looking at that code, we don't know anything about that callback. We don't know if it's invoked on the main thread. We don't know if it's invoked on a background thread. We don't know if it's invoked on a concurrent queue at all. There is no context whatsoever. And that's been the problem for eons, right? Like we all seen that kind of code, some framework that doesn't really have any context as to where this code is supposed to execute. And hopefully, either there is a command somewhere or initializer that takes a queue or something like that, at the very least, like a command that indicates, by the way, I'm going to call you on that kind of queue, so that's what you can expect. But we only know so many frameworks that do that. Most frameworks actually don't even bother to tell you. It's up to you to figure out, oh, by the way, it's firing off on some random queue I don't have no idea about. But it's really hard to reason, just looking at that, where this code executes, or at least that callback executes. So we're all familiar with what we tend to do, which is we just dispatch async to the main queue, right? Like you've done that tens, hundreds, thousands of times, and this is just like not good. This is the, like I said, this is the olden days. This should not happen anymore. I hate that. I hate that from the start. And this has a name, right? This is called defensive programming, and defensive programming is the root of all evil on the world. I hate it. This is one of the worst anti-patterns you can ever have. But it exposes really a lack of confidence in your code. You don't know what your code does. You don't know what it executes. So you're just trying something which feels safer, but there's no explanation as to why or how things happen that way. And really, like, it has other drawbacks, like it degrades debuggability because you're dispatching to another queue. Even if you're already on the main queue, right, you might lose your stack frame because you just dispatch and now you have a new stack frame to run that code again. And so you just degraded debuggability if you ever have to investigate that code. It may result in UI flickers, for example, where if you dispatch things too much, at some point we're familiar with the fact that the data might be cached, the data might be available, but then eventually, because we dispatch things too many times, the UI loads up after 50 milliseconds and suddenly your view controller just like shoves something and it looks like it flickers. But overall, it's just noise. It's just busy work. It's just annoying. It is not code that anybody, I'm sure, enjoys to work with or to write. It feels wrong, and it is wrong. So moving beyond that, again, I'm just going to introduce some conventions for the next slides. If you're familiar with the Swift Structured Concurrency SSC talks at DubDub, they refer to basically this term. So there's a main thread, obviously, that I'm going to refer with the palette emoji. There's a sea of concurrency, which is basically a pool of background threads on which code can execute, right? There's a pool managed by the runtime of SSC, and code can execute on that sea of concurrency. And there's actors, which are islands of serialization. So that island refers to an actor. So I'm going to use these emojis in the next few slides. Okay, so now we have SSC. I'm not going to introduce the syntax. We're all familiar with it. There's async, await. There's a bunch of structures. I'm assuming that you're all familiar with it. And so we write this. Like, I'm creating a task, and I want to do the thing, and I should be completely aware of where that code executes, right? Where my interrogation marks are, I should know where that executes. So can anybody tell me where that first comment executes and where that last comment executes? Does anybody have any idea? Where, on which thread, basically, that executes? Anybody want to guess? Anybody want to try?
No guarantee.
I got a shrug from Amy. And I got
your top one's going to be an inherited thread, like the
so the top one is going to be an inherited thread.
One's not guaranteed.
So bottom one is not guaranteed.
Because if you say away, means the current thread got blocked, and you can't do it in the main thread. Therefore, I assume it's done from the background thread.
Okay, so I think basically we all agree to disagree, which is bad. Right, like that's the problem, and the reason really, like Amy, I think is right, is that we have insufficient context. We cannot infer where we're running at this point. we have the same problem as before, actually. SSC doesn't solve that problem until, actually, you write it like that. And again, we're familiar with that. Now we have a context in which that asynchronous closure executes, which has been a scope, basically, which has been attributed with the MainActor attribute. And we're pretty familiar with it, hopefully. And basically, the Swift compiler will now inject specific code to ensure that these lines of code with the comments execute on the main thread, right? Like the MainActor attribute will tell the compiler that any asynchronous closure in that same scope, whether it's method functions or closures in that scope, will execute on the main thread. And now we actually have a guarantee, thanks to that, that this will actually run on the main thread, which is great. We have solved that problem. We have tagged. That's exactly what the @MainActor tag, whatever you want to call it, attribute is for. We hopefully all learned that. That works great. That now we have a guarantee just by looking at the file and by looking at the header on top, especially with Xcode 14. You can see now with the nice header, scrolling header thing, you can really see the MainActor all the time as you looked at that thing. And something to know as well is that a lot of classes from Apple frameworks have been tagged with @MainActor. For example, let's just consider one of the main ones is UI view controller. And this attribute is inherited by subclasses. So if you subclass UI view controller, all of your async methods inside your subclass of UI view controller will run on the MainActor. It is a guarantee as well. You don't have to repeat it, which is nice. So every single UI class that you write async code with will implicitly have that @MainActor guarantee. It's really great, and we love it, and I'm sure you probably are fairly familiar with that aspect. And that's one of the great advantages of SSC. But there's other syntax, and I forgot to update that slide. The thread means a color palette. I forgot. I use that as a previous emoji, so think of it as a color palette. But basically, you can tag a task closure with @MainActor in, and that will execute that single closure on the MainActor. You can tag the function, the method on the class myClass, just this method as @MainActor, and only this method will execute on the MainActor, and the rest will execute who knows where. And then obviously the last syntax, which is that the MainActor is tagged on the class. But again, like the attribute applies to the scope. So you just go down, and whatever is in that scope has that attribute inherited. The compiler looks at that file and can generate the proper code so that it guarantees that code will run on the MainActor. Okay, so now next problem. So again, can you tell me where the first line and the last line execute? So now we're in a class, and yeah, so same problem. It's an async function. Where does that execute? Anybody want to guess?
In background thread, because you have async code.
So you're saying a background thread because it has async code. It's a pretty good guess. Anybody wants to?
It's tagged async, so
It's tagged async, so
it's assumed somewhere, some random background.
somewhere some random background thread. Well, the answer is again insufficient context. And this time it's not about any kind of like attribute that you look in the file. What really matters, and that's what this talk is all about, that's the big reveal now, is that what you need to know actually is the compiler version. These changes depending on the Swift compiler version. So really, the answer is that in Swift, before 5.7, so basically any version below or equal to 5.6, the first line and the last line could execute anywhere. There is no guarantee, there is no determinicity. Basically, the first line will execute on whatever executor context the function is called with. So if that function is called by the MainActor, you will execute on the MainActor. If you are called by something on the C of concurrency, you will execute on the C of concurrency. If you call by an actor, you will be on that actor executor context. The last line will, again, there's no determinicity because it will run in whatever executor context the do the thing method has returned with. So if do the thing switches context and does something on another actor or whatever, you will then inherit, you will continue executing on whatever was the last executor context of that function. And so it could be whatever. And that's pretty bad again. There is no determinicity. And the worst thing is that this can introduce some very nasty bugs where, let's imagine that do the thing 99% of the time does its work on the main actor, and you test it, you're developing it, everything works fine, you're testing it, you're shipping it to prod, but it happens that 1% of the time, do the thing actually has to do something on a background thread because, oh, a cache is not hit and actually has to do some network I/O. Now you're doing that work that you expected to happen on the main thread because that's what happened when you were developing it. Actually happened on that background thread. Now you have a bug on production that you can't understand, that is hard to debug. So this is a terrible state of this terrible state of things. We don't want that. We don't want undeterminicity. This is really nasty, and this has beaten me. This has beaten other people on the field. You've seen probably plenty of blog posts talking about that problem. And if you write any SSC code using Swift 5.6 or earlier, you will get beaten by that bug. So I'm warning you very much to, at the very least, use Xcode 14 if you can, because I'm going to get to that. But also there's another problem before we get even to that, right? Like, let's say again, I'm going to do some heavy computation, and I don't want that computation to happen on the main thread. So what do I do? Like, what do I do if I don't want to execute on main thread? Like, does anybody know in SSC, how do I do it so that, okay, I know that I'm kind of coming from the main thread. What should I do in order to make that computation somewhere else? Anybody know? The answer is not insufficient context.
Yes, maybe you can provide a particular queue to the task.
So,
Part of its initializer?
no. So the answer is basically a pile of hacks. And so the real answer is really like, don't bother. Don't bother. It's impossible. Like, there's ways to do it, but it's so hacky that really there's no way. Like, you don't want to even try. And that's, again, bad, right? I want to start doing work of the main thread, but if I'm already coming from the main thread, there's no way for me to yield, really, and to go on another thread using SSC. With GCD, I could do that. With dispatching on another queue, with SSC, I cannot do that. And so now we're taking all of this together, right? We're packing all of that, and this is really the payoff, is that you should read this Swift evolution proposal. I don't know if you are familiar with this specific number, but this is critical to work with SSC moving forward. It is a fairly small proposal. It can be read in like 2 or 3 minutes, but it is so important to read and to understand. Its title is Clarifies the Execution of Non-Actor Isolated Async Functions, which, what does that mean? So what it is, it's not really like a proposal like, oh, we're going to introduce new syntax or new keywords and then the language somewhere. No. What it says, like, we messed up. That situation that I showed you before where we don't know where things execute is bad. Let's just give guarantees in the next version of Swift, which at the time was Swift 5.7, so that we know at any point where things will execute. It will be deterministic. So it's not really an addition to the language. It's more like an errata. It's like, oh, we messed up. Sorry, we're just going to fix that problem for you. It recognizes that the previous behavior I showed you, where we don't really know where things execute, it depends on who calls you and what you call and where it executes at any point in time. That has problems that is unpredictable, but also it can have overhangs. What if you're being called from an actor and you are doing heavy computation, like the main actor, and heavy computations, you are holding that actor back because you are holding that actor cannot process any other information while you're doing that computation. It's a problem they call overhang. You are grabbing that executor context for too long, and therefore concurrency is poor because you don't need to run on that actor queue, but you are doing it somehow because the runtime doesn't help you in that case. And that's bad for performance. That's bad for responsiveness and all of that. So the solution that they came up with is simple. It's like, always run non-actor functions on the generic executors, always. So if something is not in an actor or something tagged with main actor or whatever else global actor, it will always run in a sea of concurrency. That's it. That is now deterministic. It will always do that, which solves all of our problems. We know where it executes, and we have the main thread if we need to, unless we tag things by at main actor. If you think about it, one of the drawbacks of that policy, because we have so many context switches all the time, because if we're on the main actor, now we have to call a function which is not isolated, we have to switch even though we might not need to. It's a bit of like overhead every time we do that. So the drawback is potentially that there's going to be at runtime more switches between what they call executor contexts, which you can interpret as queues. So a lot more switches back and forth at runtime, which has obviously a cost, a CPU cost doing that all the time if it's too much. But to the advantage of like I said, that it still increases concurrency. So in the end, you might actually end up better because you are, again, spreading your work across multiple threads, multiple cores, which in the end might be a wash, even though you're spending more time switching between contexts. So I encourage, once again, I'm doing a poor job of summarizing it, but that's basically in the gist of it, that's what it says. It's like, we are making that trade-off of like, whenever you're not actor isolated, you're just going to run on the sea of concurrency, and that's it. And so now we have an answer to that problem, which is that starting with Swift 5.7, you have an async function in a, let's say, a class that is not an actor, that is not tagged with @MainActor or anything like that. That function will always run in a sea of concurrency, whatever you are called from, or wherever you call from, or whatever do the thing does and returns from. It will always context switch, and you are guaranteed that it runs on a sea of concurrency. And that's great. I think that's great because guarantees in code are good. We like deterministic execution, right? I hope so. And yeah, like just to reemphasize things, it's all about local reasoning. To come back to things like before of like, when you look at code, when you look at a class, you can now really, that's all the context you need to know where code executes, which thread it executes on. You don't have to like know the architecture of the app, know who calls you, know what you call, or anything like that, like we had to do before. All you have to do is look at that file, hopefully. If it's an extension, it's a bit complex, but and you can see everything you need to know. If it's a class, it will run in the sea of concurrency. If it's @MainActor, it runs on the MainActor. If it's an actor, it runs on its own executor context, which is serial. I mean, there's problems of reentrancy and all that, but I'm not gonna get into that, right? But yeah, it's all about local reasoning. Local reasoning is good. It removes a lot of the burden, intellectual burden of understanding code, understanding an application. You don't have to understand everything in order to work on a piece of code. It just declares itself in one file or one function. And that's pretty much it. That's the end. I just want to add two little blog posts that have been written in the last few days from Ole Begemann, which is pretty famous, I guess, in the iOS development circles, who actually like has stumbled upon that exact same problem in the last couple of weeks, and has written blog posts about that, about like, I don't know where things execute and how are things on the MainActor, and oh, by the way, this Xcode 13 has this behavior and Xcode 14, which ships with Swift 5.7, has this other behavior. And he's done the research, he's done a lot of like thorough investigating as to how the compiler works and the runtime works to enable this behavior. But even the best and brilliant minds in our community have been beat by this behavior. So my talk is a warning of like, the day you introduce Swift SSC in your code, the day you really embrace it, be mindful of this, and hopefully you're going to start with Swift 5.7, so you never have to think about it. But if you don't, then just understand that there's different behaviors between Xcode 14 and whatever Xcode version was before. At least that's the Swift compiler versions that come with it. But yeah, so, and it's, again, to just add a bit to my conclusion, it's a problem if you follow the Swift forums, which, fine. It's a constant source of problems on the Swift forums as well. Like half of the topics on the SSC that are SSC focused on Swift forums are about the same problem, like people not knowing, like, I don't understand why things are executing on that specific thread. I don't understand how I can go and execute something of the main thread. So it's a lot of confusion about that specific problem. So that's why I made this talk, in order to spread the gospel of SE 338, because this says explicitly, like, moving forward, you don't have to worry too much about that, and you will be able to reason locally about where things execute, which down the line will hopefully help you write very responsive, performant apps without trying to wonder why things are like that. You will be able to understand, okay, I understand what the compiler and the runtime are doing, because that is how the code is written, which is how code should be. And that's it.
Any questions?
Yeah, question. Let's back to start with your presentation. Okay, thank you. Let's back to start with your presentation.
Yep.
We have something we don't know which thread is running. We have to use DispatchQueue.main.async something, even though it's not necessary because you are already in main thread. Right? Will this technology help in this case?
Well, I'm saying like I have a need to run on the main thread, let's say, right? If I know my example doesn't really show that, but if I have a need to execute something on the main thread, then my only way to really ensure it goes on the main thread is to dispatch async.
No, I'm not going to ensure that it goes to main thread. The problem is actually vice versa, as you started. We are already in main thread, but the code doesn't know whether we are in main thread or not. It said DispatchQueue.main.async, while we don't need async. We just can you run the code as normally, right?
Maybe we don't know, right? Looking at that code, I'm reading that code.
How this SSC can help in this case? Will it be smart enough to figure out we're already in main thread, we don't need async? It doesn't.
But in order to know that, you would have to read the documentation, let's say. You would have to know that, oh, in the initializer of that class, I can pass a queue that then it...
This is how we started your presentation. I thought you were going to answer this question.
Yeah. Oh, no, like, I'm just saying there's no solution to that problem. There is none. SSC introduces a solution to that problem by introducing the MainActor attribute, which forces the runtime to context switch to the main thread with a simple attribute. You are declaring, right? It's a difference between imperative programming and declarative programming. You are declaring that that method or that class, everything inside it needs to execute the main actor. And you only have to write one line, and it's local to the file. You don't have to imperatively redispatch every single thing that happens. You can just declare it, and the compiler takes care of injecting all the steps to make sure it's executed.
That's a matter of coding, right? The code thing becomes shorter. That's the only thing. You don't save time.
Yeah, but
you don't make it more efficient. It doesn't do that.
It's also safer because the compiler ensures that if you write something at MainActor, there will be checks that if you are in an async context calling into a MainActor, right? So let's say you are, I'm just going to go up. I'm just going to show that, right? Like, let's look at that. That class, obviously, like the @MainActor attribute tells, actually, I'm going to show this one. The @MainActor attribute tells, by the way, make sure that this runs on the main actor. That's already great. But also, it ensures that the caller knows that it's on the main actor. So you're going to have a guarantee to run that, but then it also knows, okay, well, if the caller is already on the main actor, the compiler will know that, and it will say, okay, you don't need to add a wait, because you are executing on the same actor context. So it can be actually a synchronous call because you are staying on the same actor. So there's actually like, whereas if you're not on the same actor, it will say, no. You are calling an async function. You need to call a wait here. It's an asynchronous operation. You have to add a wait. So it gives you guarantees as well to make sure the caller has to be in a synchronous context, which it's a viral thing, which makes sure that you always in a proper context all the way through the call chain.
By the way, what is the difference between async and no async?
Because the top one is just like I'm starting the task inside the function, so I'm really like spawning a task at this point. The function itself doesn't need to be async. I'm just creating the task inside there, but you can basically have that syntax. It's as an attribute of the closure itself.